Today we're going to be looking at the flexural design considerations. Now here we're going to be considering bending inclusive of lateral buckling. Now for designs based on permissible stress philosophy, bending is checked by applying the basic theory of bending. Now this was initially discussed, if I'm not mistaken, some 2 lectures before, and we also had an assignment on that. So I believe this should be straightforward now, the bending theory. Now with respect to timber, this must take into account the relevant modification factors for exposure, load duration, load sharing, amongst others. All right, again, going back to a few lectures, we came across the different factors that's going to affect the stresses, and among the factors, the modification factors, we had, for example, if you're designing your timber, you have to consider both wet and dry exposure. So there is a load modification factor applicable there. For load duration, the time over which the load is applicable to the member, again, there's a modification factor with respect to that. In trusses, where load are being shared amongst a few truss members, you also need to apply modification factors, and so on. Now, from bending theory, we already know that the moment is equal to the stress times Z, the section modulus. Now, the section modulus is normally obtained using the formula BD squared by 6 for rectangular sections, where B is the breadth and D is the depth of the section. Knowing the applied loads, the maximum bending moment M can be calculated. All right. Now, section modulus Z about the x-axis is obtained using the formula M over the stress. All right. Now, the moment again is dependent, as we know, on the applied loads. All right. So if it is a point load, if it is a UDL, or if we've got two, both UDL and point load, we can easily determine the moment. Now the stress is dependent on the type of timber being used. All right, so South African pine will have a stress of 6 MPa and so on. So once you know the moment and the type of timber you're using, you can easily determine the section modulus Z about the x-axis. Okay, so the F denotes the permissible stress value of the material. As we said, it depends on the type of timber. Now here, the permissible stress of the material is equivalent to the grade bending stress, which is denoted by sigma mj par. All right, and this needs to be modified by relevant key factors. Now, it depends on what this particular member is being subjected to, and accordingly, the relevant key factors would come in play. For example, so what are the key factors that would need to be considered? So K2, exposure factor. All right. If we're dealing with a timber that is going to be exposed in a wet environment, so K2 comes in place. K3, if the load duration factor is of consideration, if you need to consider that. Now, if you're designing a truss, the load sharing factor K8 is applicable, as well as the depth factor K7. Now, it is to be noted that for depths of 72 millimeters or less, the grade bending stress should be multiplied by a factor K7, right? Which is a value of 1.17, right? So this is for timber of depth 72 millimeters or less. Now for depths greater than 72 millimeters and less than 300 millimeters. So within the range of 72, greater than 72, but less than 300 millimeters, the grade bending stress should be multiplied by a K7 factor, which is determined using the formula provided on this particular slide, which is 300 divided by h to the power of 0.11, right? So please note this 0.11 is a power, right? It is not multiplying directly, but it is a power, okay? So we have in BS 5268 a table specific for K7 modification factor, and which is based on this formula 300 over h to the power of 0.11. And as the height increases from 72, the value also increases from 1.17. Sorry, it decreases from 1.17 and keeps on decreasing. All right. So this is provided in the table. Now, if you've got a value which is in between, then you have to interpolate. All right. So if you've got, let's say, a value of 121, so you have to use the value of 120 and 122, and then you determine what is 121 is going to be, the K7 value. All right. So please be aware that for lesser than 72 millimeters, we use 1.17. For greater than 72 and less than 300, we have to compute the factor, and it is going to be a value lesser than 1.17. The expression for calculating the section modulus ZXX for timber members, including all the modification factors K we've listed previously, should be in line with this equation, where ZXX, the section modulus required for a particular section, would be equal to the moment calculated based on applied loads divided by the stress of the timber selected, that is sigma m j PAR, multiplied by the factors K2, K3, K7, and K8. All right, so this will result in the required section modulus for the section you need to have. So a suitable section size having a section modulus ZXX greater than that required, okay, and the required again is calculated from the above formula, will have to be chosen from tables 98 to 100 of BS 5268. Now, if you refer to tables 98, 99, and 100, you're going to have indication on whether the section being chosen is a planed section or is it a rough section. Again, you have to pay attention to what we said earlier. When you specified your timber sections, you have to be very specific whether it is the rough dimension or whether it is the finished dimensions. So when we design, we use the finished dimension, so it has to be the finished dimension that you choose from the tables. All right, so this should be clear and followed, otherwise you might have issues with other checks that you're going to do. For example, once you selected the timber section, you have to check for the deflection as well as the shear criteria. So millimeters will matter when you're checking for deflection. So you have to be very careful once again with respect to this section you're choosing. Is it going to be a rough dimension, or is it going to be a plain dimension or a finished dimension? Now, so far we've been talking about bending. Now, what about lateral buckling, which is also a very important aspect when you design members in flexure. So it is also necessary to ensure that whilst the member is bending vertically, you don't have lateral buckling failure being induced in the member. Now, how are we going to tackle that? How are we going to solve that lateral buckling? How are we going to ensure that there is no lateral buckling? The answer is very simple. To avoid such failure, the recommended depth to breadth ratio values should be in line with the table reproduced here, which is table 19 of British Standard 5268. Now, what does the table provide us with? Basically, it is a table giving us the maximum depth to breadth ratio, right? And you've got the degree of lateral support in the first column, and the second is the maximum depth to breadth ratio. So when you've got no lateral support, the maximum depth to breadth ratio should be taken as 2. When ends are held in position, the value should be 3. Now, if you've got the conditions where ends held in position and member held in line as by purlins or tie rods at centers not more than 30 times breadth of the member, then you can go for 4, the ratio. Right, so basically to sum up, the conditions here exist to provide or not to provide bracing to prevent the lateral buckling from occurring. So depending on the type of bracing to prevent the lateral buckling, the ratio is going to be different. So when you've got no buckling, when you've got no support, no lateral support, it means that the element is going to buckle laterally, right? So then you need to have bigger breadth, right? So when you provide more lateral supports, then you can see that the depth can be bigger and the breadth can be reduced, right? So the depth to breadth is higher, meaning that the depth can be consequent compared to the breadth of the section you have chosen, right? So if we may go more in depth with respect to the section, when you have no lateral support, basically we are in a rectangular section, but when we move downwards, we are more into a rectangular but slender section when we look at the vertical dimension.